today. We thank you for the gift of life. We thank you for protecting us and covering us, and for thus far you have brought us. Lord, we continue to pray for your guidance and that you will teach us, dear Holy Spirit, this new topic that we are going to be taught. Lord, we pray that we'll understand each and everything and be able to apply it in whatever we need to apply it in. We give you all the praise. We may continue to bless these teachers who give in their time for us. In Jesus' name we have prayed. Amen.
Amen. Thank you very much for that wonderful prayer. I want to welcome each and every one to our fourth lesson. In the previous lesson, I promised us that we could begin to our very first topic, to physical chemistry. And here we are looking at that topic, which I believe we all know that our very first topic is Equilibria 1. For those who have joined us for the first time, this is teacher Nyirimbibi Isaac, who will be taking us through today's session. And as usual, I want to request each and everyone to pay much attention and to keep on raising up the hand where it is not clear, because our sessions have to be very interactive so that we can be able to learn from whatever we discuss. So today we are looking at physical chemistry, and our first topic to this chapter, to this physical chemistry, it is Equilibria 2. Equilibria 1 was covered in Senior 5, third term. For those who have not yet covered it, please let's have time and we go through. As I said also previously, that let's always get the syllabus books so that we know where we are going for proper preparation. The syllabus books were shared in the group. I believe each one of us has the syllabus book for chemistry, and you know what is entailed in this chapter, Equilibria 2. Equilibria 2 has different subtopics, and the first subtopic is what we call the physical equilibria. And today, basically, in physical equilibria, we shall be introduced the introduction to physical equilibria, and then some simple introduction on RAOULT'S law. Then in our next lesson next week, we shall be expounding more on what we have learned in today's lesson. As we start off this lesson, I have a few lesson objectives, what we expect to have known by the end of this lesson. Let me have one person raise up the hand and read us through these objectives that we are supposed to achieve by the end of this lesson. I have Mugisha Henry. Mugisha Henry, unmute.
So the lesson objectives. By the end of this lesson, we, the learners, should be able to 1. Explain physical equilibrium. 2. Distinguish physical and chemical equilibrium. Then 3. Define vapor pressure. 4. State and apply RAOULT'S law. 5. Describe ideal solutions.
Okay, thank you very much. So those are some of the lesson objectives, or what we are expecting to have known by the end of this lesson. By the end of this lesson, we are saying we, the learners should be able to explain physical equilibrium. So by the time we finish this lesson, we should be able to know what physical equilibrium is. Then we distinguish between the physical and the chemical equilibria. Then we also define what vapor pressure is. Then we also are saying we should be able to state and apply RAOULT'S law. And then finally, we should be able to describe ideal solutions. As I said, this topic is is not a short topic, it is a little bit big, but today we are going to do introduction, and then we'll be able to go ahead and do research about this very topic. The good thing, we have our syllabus books. So when we go through this, I believe we'll be able to do more notes, so that next time when we are doing revision, maybe in the next holiday, it will be very easy for us to discuss all this work. Let's look at this discussion activity. Here is a nice discussion activity, and we are saying, what happens when water is left in an open container? Does the evaporation ever stop? Let's discuss our ideas. We can put our ideas in the chat, but also let me have those people who can share with us. Yeah, you raise up the hand and you share with us. Who is ready? What happens when water is left in an open container? Who is ready? By show of hand. What happens when water is left in an open container? Yes, peace and mute. Okay.
Good afternoon, teacher.
Good afternoon.
So when water is left in an open container, evaporation occurs, and the particles, the molecules of the water, some of them escape and continue to leave the container.
So you're saying that the molecules escape, yeah? Hello? Hey, peace, you're muting very fast. Mute, you unmute again. You complete your point. So number
Yes,
one, you're saying that when water is left in an open container, evaporation occurs, and you're saying that some molecules escape. Now we're
yes.
asking, when this evaporation occurs, does it ever stop at any point?
From what I understand, evaporation never stops because if we look at boiling water, there's evaporation. When we also have water at room temperature, the water keeps reducing, or even when it's covered, you notice that some of the liquid molecules stick on the side of the container. And also when we have water in ice form, you notice that some of the like there's like a gas that escapes, and I believe that's also evaporation. So evaporation never stops.
Okay, thank you very much. Let's clap hands for her. So Peace is saying that evaporation will never stop, and even Jonah is saying it never stops. Then Nari and Linda is saying, okay, very good. People are clapping hands. Thank you very much. So I'm saying that when we leave water in an open container, the evaporation will occur. And when evaporation occurs, these molecules will keep on escaping, which means it will never stop. And eventually, at the end of it all this water may end up getting complete. So here are some of the few things that we say: that water slowly evaporates into the air, which Peace has already explained to us. And they're saying that as a result, the level of water decreases with time. Then the other one was saying, does evaporation ever stop? Evaporation does not stop. Like Peace has already told us. As long as there is water and the air above it is not circulated, and so we are saying that as long as there's water and air above it is not circulated, what happens? Evaporation will not stop. But they're saying, however, the rate of evaporation may change depending on the temperature, wind, and humidity. So when we're in a dry place and we're in cold place, the evaporation in a dry place and in a cold place, it can never be the same. So That's what they're saying, that however, the rate of evaporation may change. Now, I want someone to look at this. What about what will happen when water is closed in the bottle? Because at first, we have been seeing when you put water in an open container. Now, what will happen when water is closed in the bottle? What happens when this water is now closed in the bottle? Let's explain that. Judith. Yes, Judith.
Good afternoon, teacher.
Good afternoon.
I think since the water bottle is closed and there is no interaction of the air molecules with the water molecules, there is no room for evaporation to occur. In other words, the volume of water is going to remain the same.
Volume of water. Okay, let me note your points. So you're saying that the volume of water remains the same. Okay,
Yes.
thank you. Okay, thank you, Ruth. Let me have also Namakula. Namakula, you unmute. Share your idea. Yes, Namakula.
Okay, so for me, I think when water is closed in a bottle, it will not be able to evaporate as such because okay, most times when water is in a bottle, it's added with some other gas. So since there are some factors that affect evaporation, the rate of evaporation, and one of them is vapor pressure or pressure. So, let me not use vapor pressure, but pressure generally. So it will cause a resistance in the rise, okay, or in the molecular interaction of the water molecules for it to now do what? Vaporize and move out or move on to the whatever, the bottle cover. Then I also think that it can also be based on the temperature of the what? Of the water in that bottle. So I feel like there is, to some extent or a small percentage, a bit of evaporation. Yes,
So
depending on
there
the
will be,
amount of gas which is used for the storage, the pressure that has been used in sealing the bottle.
So you're saying to the small extent, there will be
yes,
evaporation. So are you telling us, which means at the end of it all, because when there's evaporation takes place, are you telling us that now the water is going to start reducing with time?
not as such. A very small extent that it's almost inevitable. That's what I'm saying.
Okay, thank you. Let's hear from also Wafula John Elijah. Yes, Wafula? Wafula John Elijah?
Yes, teacher, good afternoon.
Good afternoon.
So, teacher, about the bottle that is closed, what I would think that at a very small extent, there will be a bit of evaporation. Because usually you if you look at such water bottles, at a point you find water droplets on that space they leave above there. But you realize that after that evaporation occurs, there are some water molecules that are going to condense back into the exact same liquid. So you realize that the rate at which the water is evaporating and condensing is actually the same. So the water level won't change, it will remain the same, to be at equilibrium.
Wafula, that is a wonderful explanation. Thank you. Can we clap hands for him? I think he has nailed it because he has explained for us the whole thing. So even the first presenters were showing us that actually the first one told us that volume of water remained the same. And even Wafula is what he's telling us, though Wafula is now explaining why is the volume remaining the same. Then this one also told us that evaporation is taking place at a small extent. But now Wafula is saying that as evaporation is taking place, even condensation is taking place. So at the end of it all, the volume of water remains constant. Let me have one person read for us what I'm going to put. Lydia, unmute. Lydia, you can unmute. Lydia, you have a question or you're going to lead us in reading this second part here? What Wafula has already explained to us, that evaporation is taking place at the same time as condensation is taking place. And I believe I've observed that in the bottles that we buy, maybe the drinking water, when you buy such a bottle, sometimes when it is the temperatures are high, you'll find there are some water droplets, meaning evaporation took place, but now they didn't have anywhere to escape from because it is tightly closed. So, meaning when evaporation is taking place, even the condensation is taking place. So when they take place, since they take place at the same time, we say that now there is no change in the volume. Let me hear from Lydia. You have a question or we move on? Lydia?
We move on.
Okay, so Lydia, you read for us these key points here. Okay.
So they are saying that water in a closed bottle. Water evaporates.
Water in closed bottle, it evaporates.
Vapor condenses back.
It condenses back. Okay.
After some time, the water level stays the same. The equilibrium is reached.
I think so. At that point, we see that the evaporation is taking place at the same time. What has evaporated, it condenses back. So I say that after some time, the water level stays the same, and here we say that at this point the equilibrium has reached. You recall we are looking at physical equilibria.
Yeah.
Are we there? So at the end of it all, we should be able to explain what physical equilibria is. All of these that we are looking at the things that we interact with in our day-to-day life, but we shall find out that at the end, these are things that we are going to be talking about in this topic. Not like at first when learners used to think physical equilibria is somewhere in the textbooks, yet we have the physical equilibria all around us. Now, let's look at this other question. I believe this one is very clear. Wafula has already explained this and those other presenters who came in. Now, let's look at this picture here. I want us to share our observation. What do we see and what can we explain from whatever we have been discussing? And then, so I want us to discuss our observation from the picture that we are seeing right here. And thereafter, we should be able to explain what physical equilibria is. Who is ready? Okay, Maga, unmute. Yes, Maga.
Teacher, I'm asking a question.
Yes, please.
Teacher, the previous slide. So, teacher, are you trying to say that? Okay, I'm asking, does the outside temperature have an effect on the condensation and evaporation of water in a bottle?
Okay.
Like, does the outside temperature affect in any way?
Okay. You keep your microphone on. Gilbert wants to answer. Yes, Gilbert.
Yes, good afternoon, sir.
Good afternoon.
The question she asked whether the outside temperature has effect on the bottle. Actually, yes, it has.
Yeah.
Now,
you explain it more so that she gets
now,
it.
now, if you look at that bottle is made up of, it is matter. So, like when the outside temperature is what is changed, maybe it is increased. Now, the bottle itself is made up of particles. Those particles will conduct that heat. Remember, particles conduct heat by that what? By that by
The
vibrating
material.
as they send to the next one. And the water inside is attached to the walls of the bottle. That means the heat from the outside will be conducted, though at a low rate since it is a plastic, but heat still is conducted because the layer is thin to the water inside. That's why actually it is simply proven when you look at the water being put in the freezer, in the bottle, a packed bottle. If you put it in the freezer after some long period of time, of course, you will find out that the water has frozen. So that means that the heat, either heat loss or heat gain, is conducted through the water bottle. That's why the outside temperature has an effect on the water.
Okay, thank you very much, Gilbert. I believe that one is very clear. So the outside temperature will have the effect, though, even if there is an effect, you see the evaporation when it takes place at the same time, the condensation will be taking place. At one point, the equilibrium will be reached. Are we there?
So now, yes.
Uh,
So teacher,
yes, please.
one more little thing. So is temperature a factor that causes water in a bottle to evaporate and condensate?
Okay, so when the temperatures are high, you look at this. If the temperature are high, they will cause this water to evaporate. If you put a water bottle in a freezer, it will cause it to, because if you leave it in the freezer, you'll find when it has changed from even a liquid to a solid. But if you leave your bottle maybe on a table here, then there is too much sunshine, you'll find out that, or when there's much heat, you'll find out that there are some water droplets coming on the bottom of the what? Of the bottle. But when this, what is happening, which means the water is evaporating, but when it evaporates, it doesn't get where to pass. Then this water, this vapor changes back to liquid. And that process, the one we call the condensation. So as this one is evaporating, the other one is condensing. So that's why you're saying that after some time, it comes, they become the same, and then we say at this point, the equilibrium has been reached.
Oh, okay, teacher, thank you so much.
Okay, welcome. Okay, so let me have someone take us through this page, and then we derive the definition or what physical equilibrium is, because that was one of the learning outcome of this lesson. Yes, Lydia.
And on the diagram, sir. Thank you, sir.
Okay.
I explain on the diagram.
Yes, what your observation from on that diagram?
So I would like you to scroll down so that I can observe where up.
Okay, there. I believe you can see now.
Yeah.
Yes. Okay.
Yes, sir.
Mm-hmm.
So according to what I observe here, we see water is in a bottle, so in a container. They are reading moisture coming to the liquid, bringing energy. So as what is in the container is exerting some energy. So energy is trying to expand the container. So for instance, if it is a bit elastic, it can stretch a bit because of the energy, the molecules of the water molecules of water that are just exerting on that bottle. So as the molecules leave as the molecules of water leave from the container, they will take up that energy through that process of evaporation, as we already seen up. So as the evaporation takes place, they will try to reduce the energy the water is exerting on the container. So that's what I can observe. Thank you, sir.
Okay, thank you. Thank you, Lydia, for submission. This one, unmute. This one. This one also give us yours. This one and Matthew. Anyone who unmutes faster can begin. Matthew, Tonics. Yes, Matthew.
Okay, thank you, teacher.
Yes.
What I observe from the diagram is that these molecules coming to the liquid, bringing energy. I think the energy, it's the factors that are surrounding the container. So when those factors come to that liquid will either experience some changes, which will make these changes will make this liquid leave the container due to those factors that are surrounded the water container. I think that's it, sir.
Okay, thank you. Finally, we have one last person. Wafula. Yes, Wafula. Elijah.
Yes, teacher. Teacher, I think since the molecules coming to the liquid are bringing energy, and if you realize at the same time they have not specified, they have just told us the molecules leaving the same liquid are taking away energy. So personally, what I think is that the rate of the forward is equal to the rate of the backward. What is coming is actually the same as what is going.
Okay, so at the end of it all, it is bringing what you are calling what?
Equilibrium. So the set of
equilibrium. Okay. Okay, let's clap hands for all these people who have submitted. At least we have everyone who has submitted, giving us a glimpse of what we need. Thank you very much. Okay, so I'm just going to add on what they have shared with us. Number one, if you look at this picture, what we see exactly, just looking at it, we see a liquid in a container, yeah? And this liquid, it is having some molecules which are living. We are having molecules which are living. We are also having molecules which are coming. And we're seeing that these ones which are living are taking away the what? The energy, while these ones which are coming, they are bringing in energy. So when this one goes away, it takes some energy, but now we have another one which is it brings back the energy. Actually, this picture is depicting what we have been looking at in the closed system or the closed bottle of water. So when you look at those blue, we are seeing the blue and the yellow dots, which are representing the what? The molecules. These are the molecules. The blue dots representing those who are coming in, then the yellow dots, which are showing the molecules which are going out. So some molecules are returning from the air into the liquid. So those ones which are returning from air, we believe now that one is the condensation which is taking place. It is due to the condensation, because when this liquid evaporates, it is going out. When these ones are leaving, they are going what you're calling the what? Evaporation. So in simple terms, we're having evaporation and condensation taking place, and we see that they're taking place at the same time. So some molecules which are escaping from the liquid into the air, this is evaporation. Some molecules which are returning from air into the liquid, we are calling this one condensation. Now, what is happening to the energy? Look at what they're telling us, that molecules leaving the liquid take away the energy. Then the molecules coming back into the liquid, they bring back the energy. These ones are bringing back the energy, while these ones are taking the energy. So what is being taken is being repressed by this process we are calling the condensation process. Now, meaning in this case, the number of molecules leaving, maybe if I can just write something here, the number of molecules which are leaving is equal to the number of molecules which are returning. I may not write it very well because of my space, but what I'm saying, the number of molecules leaving is equal to the number of molecules which are returning. What does it mean? It means that the amount of liquid remains constant. The amount of liquid remains constant. Then number two, the temperature also remains constant if the conditions don't change. That is when the other lady was asking if we change the conditions outside. If we change them, also these ones are going to change. But we are saying that if the conditions don't change and we leave the system the way it is, we are seeing that the number of molecules leaving are equal to the number of molecules which are returning. Okay, so in this case, do you think we can be able to generate what physical equilibria is, the definition from what we have already discussed? What can we explain as physical equilibria by show of hand? Jovix, yes, please. Jovix, unmute.
Good afternoon, sir.
Good afternoon.
According to the illustration you have shown, and what you've explained, I think physical equilibrium is an equilibrium that exists between different phases of physical properties, but on the same substance.
But on the same
substance,
okay,
but in different physical states.
Different, okay. Well, I can see the keywords you're giving us. Number one, you're telling us the different physical states. How many physical states have we seen so far?
So far,
which ones?
The condensation state.
Which physical states? Okay, maybe the states of matter have we seen, because different substances exist in different states. So which means we need to look at those ones which are in solid state, in liquid state, in gaseous state. So in this case, we have looked at two states. Number one, which is the liquid state, and also we have looked at the gaseous
state.
And from this, we saw that we have, at this point, we have the evaporation taking place where we're changing from a liquid to gas, condensation taking place, changing now from the gas back to the liquid. So those are two states. Okay. So I've seen the key ones there. Thank you, Jovix. Any other person? Any other person who can? Okay, Wafula, unmute. Hey, Wafula has gone off. Okay. Yes, please.
Basing on the few diagrams and the questions we have answered, I think physical equilibrium is a state where they occur at equal rates, but after occurring at equal rates, there is no change of the system's composition. That's what I think.
Pardon? What did you say?
That physical equilibria, it is a state where opposing physical processes, like the ones she has stated, they occur at equal rates. but at the end of
Okay.
it all, there is no change in the system's composition.
No change in system composition. When I check in, thank you very much, Elijah, for that submission. Okay, there's someone here who is called Fika. He's saying that in the chat, he's saying that physical equilibria is the equilibrium established between molecules of a substance in one phase and molecules of the same substance in another phase at constant temperature and pressure. Okay, okay, thank you. Then another person is saying, okay, let me see another person here. So we can keep on using the chat and then we keep on keep that discussion going on. So another person is saying, okay, Elijah, what did you say? Okay, say John Paul said, physical equilibria is a state where two different physical states of the same substance exist together and the rate of change between them is equal. Okay, I can see people are putting very nice definitions, and you can see from their definitions, they are basing actually from what we have been discussing, and they're giving us their submission. Thank you very much. Let's clap hands for all these people who have given us those wonderful submissions. Now, we can go to our next part and then we see what is saying physical equilibrium. So here we are saying that, can I have someone read for us that? Who is ready to read for us what we have presented there? Teke, someone who is having Teke. Teke? Okay, yes, please.
Physical equilibrium is a state in which two opposite physical processes occur at equal rates with no observable change. It's dynamic, not static.
Okay. Have you seen those? So in simple terms, can we be able to generate that definition? And from what they have been giving us, do you see that it is correlating to the pictures we have already seen and what these other members have been sharing with us? That in physical equilibrium, it is that state in which we have two opposite physical processes. In the previous discussion, we have saw two physical processes. Number one, evaporation. Number two, condensation. And we are saying that these physical processes occur at equal rates. And when these occur at equal rates with no observable change, and we're saying that it is dynamic, not static. When we say it is dynamic, not static, what does it mean? Maybe let me hear from us. I believe we looked at this in Equilibria 1 when we talk about dynamic, a system being dynamic. Yes, Claire, could you submit something there on that? Claire? Claire West, yes. Mm. When you say it is dynamic,
Means like continuous.
Your voice is very low. If you could increase. Yes, please.
It means like it continues, it does not stop.
It continues, it does not stop. Okay, thank you. Is Lydia adding something on that? Lydia, you can unmute.
Action dynamic, I think it meaning one position.
Yes?
I think on dynamic they are meaning one position. They remain in
That
one position.
it remains in one position.
Yes.
What about static?
Static, it continues.
You see, there are these ones, static. When something is static, But now this time around we are saying dynamic.
Okay, I'm sorry.
Uh-huh.
For dynamic, it continues moving. It
Okay,
continues
thank
and
you.
motion.
Okay, thank you. Thank you for that submission. Maybe unless we have another person with a submission or these hands are for questions. Okay, Naruyinda, tell us. Naruyinda,
Good afternoon, sir.
good afternoon.
I think dynamic, it means that like equilibrium can be attained from either direction.
Either direction. So when you talk about in a layman's language, when you say this system is dynamic, so do we mean that it is moving in all directions?
Not all direction.
Uh-huh.
Meaning like the equilibrium is equal, eh? Meaning the reactants can form the products and also the products can form the what? The reactants.
Okay, thank you. Yeah, that is good. Yes, that is good. Maybe unless Ruth wants to add, but that submission is very good. Okay, so you're saying that in that case, if it is an equation reaction, the reactants keep constantly form the products, and products can form back the reactants. So that's what we are saying that it is dynamic. In simple terms, it is constantly changing. It is not fixed. It is not static. It is constantly changes, but as it changes, we are saying that as is changing maybe from condensation to evaporation, from evaporation to condensation, it is taking place at equal rates. It is taking place at equal rates. There is no observable change in whatever, but it is continuously changing rather than fixed. That is something which is dynamic, continuously changing. But for physical equilibrium, it is continuously changing at equal rates, and it is happening between the two opposite physical changes. So that is what we are calling physical equilibrium. I hope it is very clear at that. Okay, now we can move on to our next part where we look at some examples of physical equilibria. Because we are seeing that they are different, uh, we are saying that there are different physical processes which are taking place, and here we have some examples of physical equilibrium. Let me have someone take us through this, and if you have any other submission on examples and finding out what physical equilibrium is, you can still submit. Then can I have someone take us through these examples, and if you have any other extra, you can still add. Who's ready to take us through that? Oh, okay. But as we finish this lesson, okay, Jovix, you can take us through. I encourage us to do research so that when we come, we are discussing just. Yes.
Okay. The
Yes,
examples of
Jovix.
physical equilibrium, first of all is liquid to vapor, then evaporation to condensation, just in brackets. Then the second is solid to liquid, that's melting to freezing. The third one is solute, equilibrium to solution, in brackets dissolving to crystallization.
Do you think you can add something to help other people who are maybe just joined to understand what these examples are meaning, or just something addition, some explanation maybe somewhere?
Just I can add on that all these exist in different physical maybe states. And it does not, in this equilibrium, there's no chemical change. So it only involves physical changes like those of solubility or the changes of the physical changes like a solid changing to a liquid. And we all know that it's like a phase because there are phases, different phases. Then I can give an example of a phase diagram of water. Because water can change from sublimation. Sublimation is from solid to water vapor. Then it also can involve in a vaporization, whereby this vaporization is from liquid water to water vapor. So there are different physical states occurring in this equilibrium.
Okay, thank you. So you are trying to tell us the one for water where it is changing from solid, maybe an ice, changing to liquid, and maybe this liquid is changing to vapor, and this vapor can still turn back to liquid. So yeah, that is good. Thank you, Jovix. I'm seeing Dr. Peace. You can also Peace.
Teacher, I'm just adding on something small
Okay.
for that just joined. It's like for the first example, the liquid is changing to vapor form, but the process occurring at equilibrium. So in brackets, they're trying to explain evaporation is at equilibrium with condensation, which means that the liquid part of the water in the system is equal to the vapor part. Or what I'm trying to mean is that the rate at which the evaporation is occurring is equal to the rate at which condensation is occurring. So, which means that the whole process will take place at equilibrium. And we know that for equilibrium reactions, they may exist like as if there is no change in the overall reaction. Then for the second example, for the solid to liquid, the melting is at equilibrium with the freezing process. So which means that as this solid is trying to change, in other words, the rate at which the forward reaction is occurring is equal to the rate at which the backward reaction is occurring. Which means that as this solid is trying to melt, to turn to a liquid, again, the freezing is also taking place at the same rate. So the process will not stop since the reactions are equal. Or at equilibrium. So the reaction will not stop, but it will, that's what we refer to as dynamic. It will continue constantly. So there will be a constant continuation of the whole process. So which means that we shall keep on having both the solid and the liquid in the same container, but you may not see like any change in the overall reaction as the solid is converting to a liquid. Then the last one, it is still the same explanation. Dissolving is at equilibrium with crystallization.
Thank you very much. Can we clap hands for Peace for leading us in that? That is a good explanation, and I believe it was very clear. Thank you. There are people clapping. Maybe Samsung. Samsung, you have something? Yes, Samsung. You are mute. Samsung 0S07. Yes.
So for me, my question is about, is crystallization the same as sublimation?
Are you talking sublimation? You're talking about sublimation and crystallization. Samsung, are you saying this? You're asking, is sublimation the same as crystallization? Samsung? Maybe London. London, you and Newton, they explain those two. Tell us the difference. Samsung, are you getting now?
Yes.
So you're asking whether sublimation is same as
Yes.
crystallization. London, okay, London is going
Yes.
to explain. Yes, London.
I was not going to explain. I also had a first. The way Ruth was explaining, it seemed as if she was saying that evaporation and condensation were taking like we're happening at the same pace, like at the same time. Now my question is it like that, or it's like the energy used to change something from solid to liquid is equivalent to the energy required to change something from liquid back to solid?
Okay, so you're talking about the energy, then you're asking whether they are taking place at the same time. Yeah? Are they
According to
taking place at the
Ruth's,
same time, or it is one taking it is in terms of energy? Energy which is maybe being taken out is equal to the one which is coming in.
yeah.
Okay. You keep on, and maybe Peace can explain that. Peace, you explain that.
What I can say about his question, actually, I just wanted to answer the other previous question of sublimation and crystallization. But let me
Okay,
first
first answer that. So whom am I going to
So
answer first?
the second one first.
Okay.
About so he's asking about I explained and I'm like evaporation is occurring at the same time with condensation. So these things, it's like the explanation is quite similar, but it depends on the way you have achieved the concept. Yeah. So evaporation is occurring at equilibriums. For chemists, we know that something to be at equilibrium, it's like since we represent with partial arrows, the rate of forward reaction in most of the cases is equal to the rate of backward reaction. So this means that in the system, we shall have both of the processes occurring. But if again a person...
Maybe Peace on at that point, maybe someone was
Yes.
asking initially before, because this equilibrium does not happen immediately, isn't it? You
Yes.
find out that the process starts, and then at the end of it all, the equilibrium is reached at a given point, and then when the equilibrium is reached, it's when those conditions of equilibrium work. So when you put at this, you recall we are looking at examples of physical equilibrium, meaning we are looking at these phases when they are in equilibrium state. But initially, of course, when it is beginning, it is not in equilibrium, but equilibrium is achieved at a given time.
Yeah, so like the other example, the water bottle we gave, the closed water bottle, yeah, it brings it up there because it will evaporate, but then after some time, the
Yes.
vapor will condense and it restores back the equilibrium. So
Yes.
then, yeah, the equilibrium will then be reached. So about
Yes.
the concept of energy, because I heard him talking about energy stuff, what. About that content, the whatever concept of energy, it's like as this as I can explain it, like as there is formation, if there is formation of a bond, there is always release of energy, and when there is breakage of a bond, there is always absorption of energy. So that's why when you're boiling water, you need to apply heat. In other words, it is like an exothermic reaction. You need an endothermic reaction. You need to apply heat, since you need to break the water molecules to form the vapor form, which is now a lighter state of matter compared to the liquid. So as you're breaking the bonds, there is that energy that is released. Then again, that same energy in the same water bottle, I'm still referring to the same water bottle, that same energy that is produced as the water molecules condense again, is the same energy that again may be used to break the water molecules again so that evaporation may occur. So keeping the whole system at equilibrium. So that's what I can say to answer him. Maybe teacher, you can add on more on my explanation.
Okay,
Yes.
thank you very much, Peace. I believe now we are good to go, but maybe this one was asking sublimation, crystallization. I believe it is very clear on when we talk about sublimation, that is changing from what to what?
So for sublimation, it is just changing a solid direct to a gas without passing through the liquid state.
Solid to a gas. But also you call a gas when it changes back to solid, it is also known as sublimation, isn't it?
Yeah, is it I had another name, or why it is deposition, or what? I don't know, maybe it is another
Okay.
name. Maybe.
Yes, okay. So we can have that. Okay, the major one is solid to gas, though in other times we have other name, but of course at another level. Though now at A level, we can have also that one. But normally we have those key processes, the sublimation from a solid to a gas. Then what about crystallization?
So for crystallization, it's all about something like a solute appearing in solution form, maybe salt dissolved in water, and you need to change that solution to again gain back that salt. So in that process of trying to boil or crystallize that solution, maybe that salt solution, as you apply heat, the water vapor evaporates off to retain back the solute. So that process is called crystallization. Then dissolution is that process when you have a salt and you're dissolving it in the in enough amount of water that can reach the dissolution point in such a way that all the solute has dissolved to appear in solution form. So that's what we call dissolution. We always do this. The daily life example is when we are preparing tea. Dissolution always occurs because we dissolve sugar in hot water to make tea. Then for
Okay.
crystallization, yeah, salt mining, they mainly use that crystallization method.
Okay, thank you very much. I think you have been very clear and the explanation very good. Unless we have anyone with a question, maybe to concretize more on sublimation, we're saying that majorly when you talk about sublimation, it is moving from solid directly to a gas. We say that is sublimation. Then when we talk about a gas to a solid, we use different, we have some different terms where we can say it is desublimation, you can say it is desublimation, or we can say it is deposition, or we say it is deposition. So you have those two ones. Let me hope that one is very clear for the one who was asking about that. So as we continue to look at physical equilibria, these are different phases that we shall be looking at. The one which can be a liquid to a vapor, or a solid to a liquid, or solid to a solution. And we said as we go through all this, we shall not forget what we have already talked about as physical equilibrium, that state in which two opposite, that's why we're saying that we are having two, not three. It is two opposite physical processes occurring at equal rates with no observable change, and this whole process being dynamic. So that's why we're saying two processes that we are talking about, a liquid and a vapor, a solid and a liquid, and then a solute and a solution. Let's move on. Now, physical versus chemical equilibria. Let us first digest this. What can we talk about this? Physical versus chemical equilibria. How can we differentiate between chemical equilibria from physical equilibria? Anyone with a submission on that? That's what we want to discuss now. We said by the end of this lesson, we should be knowing what physical equilibria is and also differentiate between physical and chemical equilibria. Yes, Harmony.
So, for me, what I know about chemical equilibrium, it's basically equilibrium established between chemical reactions. Two of them. We have the forward reaction, then the backward reaction. But most of the other things are the same. It also deals with equal rates, but of those chemical reactions. But then if you're looking at physical equilibrium, as you have discussed earlier, it deals with having physical states, physical processes in equilibrium. You're having the difference is that here you're dealing with phases, while the other side you're dealing with chemical reactions. That's the difference I know about the two.
Okay, don't mute. Don't mute. You can take us through still. That is a good submission. Maybe you can just move on and you take us through those points which I've highlighted. And I believe that's exactly what you have told us. Maybe just take us through and we get done with that.
Physical equilibrium, the first point is no new substances formed. And then secondly, it deals with the physical change. Then for chemical equilibrium, new substances are involved and chemical reactions occur.
And which explains exactly what you have already explained to us. So these other things are the same, but where we see a difference is that in a physical equilibria, there is no new substance formed. In simple terms, it is a physical change that is happening. And we know physical changes, these ones here, we're looking at these temporary changes where no new substance formed. But here in a chemical equilibria, we are looking at a new substance is involved compared to what we are looking at in the physical equilibria. And then we're saying that the chemical reactions occur. Okay, so that is how we can, okay, Marga has a question. You ask a question then.
Okay, so teacher, my question is about the reversibility and the irreversibility. So for physical equilibrium and chemical equilibrium, are they both reversible? Like I'm not understanding. Okay, how we started this lesson, we are talking about the evaporation and the condensation of water in a bottle. That is a physical equilibrium. So now for chemical equilibrium, we all know there are reversible reactions. So now, like, are they all reversible? Yeah, that's what I want to know.
Oh, that is a good question. And I see Lydia wants to answer. You can keep your microphone on. Yes, Lydia.
Oh, thank you, sir. I think they're reversible. Because we see on reversible, they are reversible. Okay. Or the reactants can form products and then the products can again form the reactants.
You give us an example and I put it down here.
So for example, on physical equilibrium.
For chemical equilibrium. For physical, she said it is okay. But now what about on chemical equilibrium?
So we can use the example of nitrogen gas reacting with hydrogen form ammonia.
Ammonia gas. We need to learn how to balance. When we balance, what we have here, we have a 2 and then a 3 here, isn't it? So, is it a full allo or a reversible allo?
It's a reversible
like
allo.
that, yeah?
Yeah.
Okay, so Maga, I want you to be on there. So this is, we see here a new substance is being formed, which is ammonia. And I believe ammonia has different bonds, which are, these ones are different completely from nitrogen, different from hydrogen. So there's a new substance formed, but when we do this one in a maybe when you do this, you find out that still this one which is being produced can form back. Ammonia can still form back the reactants, nitrogen and hydrogen. Nitrogen and hydrogen can still combine to form our product, which is ammonia. Lydia, you wanted to add something?
So, that's it. I wanted to say that ammonia can again decompose to form nitrogen gas and hydrogen gas.
Okay, thank you. Thank you very much. Bolanzi and then Silver. Okay, Bolanzi has gone. Onyango Silver. Unmute. Onyango. Onyango. Onyango, you unmute. Okay, Bolanzi, unmute. Bolanzi.
So, sir,
yes, Bolanzi.
I wanted to ask that when you're dealing with physical equilibrium, you said we don't have new changes, we don't have new substances formed. Was it? It's like that's how
No
I
new
got
substance
you.
formed. Yes, it is on the screen here. We are seeing what happens in physical equilibrium and what is happening in chemical equilibrium. Yes, please, Bolanzi.
Now, my question is, if I'm turning water to a solid, for example, ice, are those two different substances?
Okay, Bolanzi, keep your microphone on. I want Samsanga to answer. Yes, Samsanga. Samsanga, unmute and answer that question. Okay, Eustia, you answer. Unmute. Eustia. Okay, yes. Good afternoon. So, Eustia, what you're explaining now, you're helping us understand if water in liquid form is changing to ice.
Yes, teacher.
So they are asking, isn't this one a new substance being formed?
Okay,
And
the reason why it called
the
reason why they say that in physical equilibrium no new substance is formed is that even if water ice in solid form is still called water, and also water in gaseous form is called vapor. So it still remains water.
What makes it the same as this one? Why is it not a new substance?
It is just a solid. It has changed the state from liquid to solid, but it remains water.
Okay, so Bolanza, are you getting that? That what is changing is that in liquid, the particles of water are a little bit spaced, while in ice, they are compacted by the same particles. They are same particles, but they have come together, closer together. Are you saying that, Bolanzi? So the particles here, they have come together, while here they are just spaced a little bit. Then when you come in vapor form, now there the particles are more spaced, but the same particles.
So, sir, my other question is, can we have an example? For chemical equilibrium, they gave an example of nitrogen and hydrogen forming ammonia. So, what do we look at as the new substance?
Oh, new substance. You see, when nitrogen and hydrogen combine, they form ammonia. Ammonia is a different substance, totally different from hydrogen and nitrogen. You can see it is forming totally new substance. This one is having both nitrogen and hydrogen. Here we had only nitrogen separate, we had hydrogen separate. So ammonia becomes our new substance that is formed. Yes.
It's clear, sir.
Okay, thank you. Ruth Namakula. Ruth Namakula. Hey, Namakula Ruth. Samsung, you still have your hand up. Balance, you can now put down the hand so that I get to know who is having a question. Yes, Samsung.
For me, still on this thing of physical equilibrium and the chemical equilibrium. For physical equilibrium, yes, I agree on the reversibility. But now when it comes to chemical equilibrium, we see that for a chemical equilibrium, yes, we are seeing that there's some substances are reversible. But to my own understanding, I think under chemical equilibrium, there are other substances that are irreversible.
That are
Irreversible under
irreversible.
chemical equilibrium. Yes, under
Now,
chemical equilibrium.
now first look at this. If you
Where's the teacher?
Hello.
Trisha.
Where is Kaiser? Kaiser? Let's tell Kaiser to do something. Tricia. Tricia? Tricia, let's mute other people so that we can have the discussion move on.
Is you woman. That sneakers can be the window to someone's soul.
Tricia, please. Tricia, can you mute these other people? Okay. Is Tricia alone? Tricia? Hello, Ruth, can you hear me? Okay. There are some people have started writing on our screen. Tricia, can you first unmute and I hear from you, because we need to change some few settings and stop people from writing on the screen. Tricia? Tricia? Tricia, please unmute and then we can see how to move on very well. Hello, can you hear me? Let me see in the chat whether everyone is getting me clearly. Okay. Someone is saying we can continue. Okay. It's all right. Maybe Tricia can help us and disable the notations so that we don't have people start writing on our screen. When we clear that, we shall be able to move on very well. Okay, let's look at something small about vapor pressure, and then we can see how to move on. So we have already looked at examples of physical equilibria, and we want to go through vapor pressure, and then we can move on. Claire West, there are those who are writing on our screen. I would like us to see how best we can stop them. Okay, sorry for all this interruption, but I can see the host has, okay, good. It's all right. Yes, Bolanzi, you can unmute. Bolanzi, unmute, and then we move on. Yes, please.
Sir. Sir.
Yes, please, I can hear you.
Sir, I'm actually requesting.
I
don't know whether it would be okay if maybe probably we get those notes just in case we fail to finish up, because the topic looks new to me.
Yes, these notes, we normally share them in the group. So at the end of it all, you'll be able to follow the recording for those who have missed from the beginning, and then you can be able to follow. They will be able to share these notes in the group. Don't worry about that. Yes, this is our new topic, physical chemistry, and that's why we said we need to take more time as we do this introduction, so that next time it becomes very easy, but also it will help us to go ahead and do research. On the remaining learning outcomes. So one thing I want to encourage you is to continue. There's a book which we shall share in our group for Senior 6, so that we are able to also make more notes about the same topic. So make sure that you're very keen, and that the good thing you have been there as we are doing the very introduction, and now we are on these examples of physical equilibria processes. So don't worry about that. Okay, we can move on, I believe, now. Sorry for that interruption for a few minutes. It was network here, then we got off from being the host. Okay. Do you have any other person with a question? Any other question, or we move on? Bolanzi, take us through this slide about vapor pressure.
Vapor pressure. Vapor pressure is the pressure exerted by vapor molecules when a liquid is in dynamic equilibrium with its vapor in a closed container. Is everyone hearing me?
Yes, the network is just disturbing, but I believe you're very clear. Move on, please.
Vapor pressure is the pressure exerted by vapor molecules when a liquid is in dynamic equilibrium with its vapor in a closed container.
Now, here there are some key things that we are looking at. Now we are looking at vapor pressure. You recall from where we started by understanding what physical equilibria is. Then we looked at the difference between physical equilibria and chemical equilibria. And then we have already seen that physical equilibria is between two processes, where we have seen that we can have the liquid to solid, we can have a liquid to vapor equilibria, and now we are saying that when we come to vapor pressure, now the vapor pressure is that pressure exerted by vapor molecules when the liquid is in dynamic equilibria with its vapor in a closed container. So which means in this case, we are looking at it is a liquid and a vapor. But there's something that they have told us in a closed what? Container. So we're exerting pressure on this which is closed, and they're saying that this pressure that is exerted by vapor molecules when a liquid is in dynamic equilibrium with its vapor is the one we call a vapor pressure. And we say that when we call something, we say something is dynamic, meaning it is in the it is continuous. It is not static. It is not constant. It is continuous, meaning if it is liquid vapor, the liquid is changing to vapor as also vapor is coming back to the liquid, but they have reached at the equilibrium point. So that is the one we call the vapor pressure. Of course, right now, we are getting a glimpse of each part as we move on a little bit faster, but this is a glimpse, it is helping us to open our minds. That when we meet vapor pressure in the preceding notes, we are able to know what vapor pressure is and even how we can apply it. So that is what we are looking at basically. Unless, Bettina, you have a question, Bettina?
Yes, teacher, about the definition of vapor pressure.
Okay.
Like, I came across a definition that was saying vapor pressure of a pure substance is pressure exerted on the vapor over the surface of at a given temperature. So I don't know, is it still applicable
That?
here? It was like vapor
You pardon
pressure
that one?
of, it is the pressure exerted in the vapor over the surface at a given temperature. So I don't know.
Over a surface at a given temperature.
Yes.
Okay, so it is not being specific at any given temperature, and you are not telling us that either it is in a closed system or anything of that sort. So vapor exerted by so yes, at a given temperature. Good. But now they are not talking about whether it is in any equilibrium. Because another person can say vapor pressure is a pressure exerted by the vapor of a substance when it is in dynamic equilibrium with its liquid or solid at a given temperature. So a clear breakdown, the key ones we are seeing here, it is in a closed container or in maybe that system where it is closed, not allowing maybe the molecules inside to get out. So in that system which is closed, because that is the key thing that we are seeing in this case. And there's another key one we are seeing there is that maybe the key point we can note at that point is that at the same time, vapor particles return maybe to the liquid at the same time. And we are seeing that the rate of evaporation is equal to the rate of maybe condensation. That is if it is between a liquid and a vapor. So the pressure due to that vapor at this point is the one we call the vapor pressure. When all these 3 points are there. Number one, in a closed container. Number two, we are doing it at the same time where vapor particles return to the liquid. Number three, when the rate of evaporation is equal to the rate So we are saying that we can have another way we can define vapor pressure, but there are keywords that we don't need to leave out. Number one, we have seen that it is that pressure which is exerted when we are putting, maybe it is a closed container or we are looking at a closed system. That is number one. We're looking at closed. We're doing it in a closed container. That is number one. Then number two, it is happening at the same time. Now, when you say at the same time, if it is between a liquid and vapor, meaning the vapor particles return to the liquid at the same time as the liquid are going back to vapor. So that's condensation taking place and evaporation. So what does it mean? It means that when the rate of evaporation is equal to the rate of condensation and the dynamic equilibrium is established. So that is another point. The evaporation is equal to rate of condensation, and at this point, the dynamic equilibrium is reached. So I say that that kind of pressure, which is due to that vapor at this point, is the one we call the vapor pressure. So vapor pressure depends on things like temperature. It depends on temperature. That's why we are saying that that definition she was giving us, it is also very correct. Allow me first clear these people who are writing on our screen. Let me hope. Okay. Oh. Okay. So do you have any inquiry about vapor pressure? Anyone with an inquiry, then we can move on. Any person with an inquiry on vapor pressure? Anyone? Maga? Yes, Maga?
Teacher, I'm
Let's have
requesting for your
Maga.
pardon. Yes, teacher, I'm requesting for your pardon on that part of closed container. At the same time, I've not understood it very well.
Okay. So here we're saying that to give more light on vapor pressure, the key points that we're looking at, we're saying that the vapor pressure is that pressure exerted on that number, it exerted when, number one, we are looking at in a closed container or that closed system. And they are saying, in this case, we're saying that some liquid particles, in this case, there are some liquid particles escape into gas phase by evaporation. They are going to evaporate, but it is within the what? Closed container. Meaning, if it is in a closed container, at the same time, the vapor particles will return back to the liquid. So we are saying that it is a closed container where evaporation is taking place. At the same time, also condensation is taking place in a closed container. And we're saying that evaporation and condensation are taking place at the same time. When evaporation is taking place, even the condensation, it now follows, takes place. And we are saying that when the rate of evaporation is equal to the rate of condensation, that is where we are putting emphasis. When the rate of evaporation is equal to condensation and the dynamic equilibrium is established, that kind of pressure we get is the one we call the vapor pressure, of that system. So it is within the closed system, happening at the same time, and dynamic equilibria is established. Let me hope we are very clear at that point, and then we can move on. Maybe one thing we added is that this vapor pressure depends on temperature. It depends on temperature. So we need to know this one. We need to note that one. Okay, can you move on? Maybe since your microphone is on, you can take us through our next part when we talk about the dynamic equilibria in liquids. I've been talking about dynamic equilibria. Now let's talk about it a little bit here. So we are saying that dynamic equilibria, take us through those points on dynamic equilibria. Those ones, yeah.
Okay, dynamic equilibrium in liquids. Molecules escape from liquid. That is evaporation. I think we all know that.
Okay.
So the next point is vapor molecules return to liquid. That is condensation. Like for example, we can use that example of the water cycle from our primary level. The part whereby the water evaporates. So to form those clouds, then the condensation part, then it rains. I think that's an example we can use. Then the other point, the rate of evaporation is equal to the rate of condensation. That is to say, like how we were explaining that, I think we can use the other method of the bottle, the one we started with, that the same that evaporates is the same water that condenses to come back to form that water.
Okay, so in simple terms, here we're trying to understand what dynamic equilibria is in liquids. So with this dynamic equilibria, the molecules escape from the liquid, and that one is the one we call evaporation. Now, when evaporation takes place, the vapor now molecules return back to the liquid, which we are calling condensation. So dynamic equilibria, the whole of all these two processes, they keep on taking place. Dynamic, we say that when you say dynamic, it is continuing, not constant. It is keeping on taking place. It is continuing, taking place. It is not constant. It is not static. So we're saying that these two keep on taking place, and at this point, we are saying that rate of evaporation is equal to the rate of condensation. Okay, maybe you can continue to take us through these two factors that affect vapor pressure. You can take us through those also, and then Gilbert also can unmute and take us through the next part as we come to the end. Gilbert, you unmute, you take us through the next part. But after Mag will first take us through those factors. There are three factors.
Okay, factors affecting vapor pressure. One is nature of the liquid. Like nature, what something is made up of, I think it's nature. Like how it appears or what it is comprising of, I think, about the nature of a liquid. Then strength of the intermolecular forces I think the forces that are joining the forces in the liquid, joining the molecules of the liquid, I think their strength also affects how vapor pressure will be occurring in that specific liquid. Then the other one, we have temperature. So this one, I mentioned it earlier, that vapor pressure is affected by temperature. So if there is a high temperature, there will be a high vapor pressure. So likewise, if there is a low temperature, there will be a low vapor pressure. Yeah, that's what I think.
Okay, thank you very much. Now, when you talk about the nature, here when you look at the factors, we're looking at majorly these two. The nature of the liquid and maybe this one, which is the temperature. And when you talk about the nature of the liquid, this is where we talk about these intermolecular forces of attraction. If you look at different liquids, maybe like petrol, water, ether, they have these ones. You'll find out that the intermolecular force of attraction for petrol and the one for water, they are not the same. So that one also affects, because how? They're saying that liquids with weak intermolecular forces have high vapor pressure. That is for weak intermolecular forces. For example, if you talk about petrol, if you talk about ether, these ones are liquids with weak intermolecular force. Now, when you talk about liquids with a strong intermolecular force of attraction, for those ones with strong, for example, if you talk about water, the stronger the intermolecular force of attraction, the lower the vapor pressure. And the weaker intermolecular force of attraction, and then there I will say the vapor pressure becomes high. So the intermolecular force of attraction are the ones which we are looking at when we look at the nature of the liquid. Now, when you talk about the temperature, you know very well from right away from senior one, when you're looking at states of matter and you're looking at the kinetic theory of matter. So when you look at that, if temperature is increased, even the speed at which the particles move also increases. So we're saying that increase in temperature leads to increase in the vapor pressure. How? Because the higher the temperature gives particles more kinetic energy and so more escape into the vapor phase. I believe that one becomes very clear. So if the temperature increases, the particles gain more kinetic energy and therefore more escape for the particles into the vapor phase. So that's how we can explain those two factors that affect vapor pressure. But also we can have maybe another factor, the presence of dissolved substances. Or we can say presence of impurities, because if you have water and there's any other substance present in water, that one becomes an impurity. So we are saying presence of dissolved substances. This one can also affect the vapor pressure of a substance. Anyone with an inquiry on that? Wafula Elijah, you can unmute.
Yes, teacher. I was inquiring, basing on the nature of the liquids and the examples you've given us, for instance, petrol, water, can a concept of flammability come in?
Of what?
Depending on the vapor. Flammability.
Oh, like a liquid being flammable.
Yes, sir.
What causes this liquid to be flammable? Hello? Hello? Hey, you have gone very fast. Fuller, you have muted yourself. You can unmute, please.
Yes, sir.
So you're telling us on the nature of the liquids. Can you put a point on flammable and non-flammable? Anyway, we're seeing water and petrol. So it's not that we are considering to look at the explanation for the nature. The explanation for the nature of the liquid is basically coming from the intermolecular force of attraction. So we are saying that if the intermolecular force of attraction is strong, how will it affect the vapor pressure becomes low. If the intermolecular force of attraction is high, the vapor pressure becomes high. If it is weak, the vapor pressure is high. You recall the definition that you have gotten from here, what vapor pressure is. We say that it is the pressure exerted by vapor molecules. So, which means the ability of a substance to go into vapor form will give it the high chance to have, so which means the vapor pressure will become high if this substance has that ability to form the vapor. Why? Because the vapor pressure is exerted on vapor molecules. I don't know whether you're getting that one.
Yes, teacher.
Now, what does it mean? It means that if a substance has weak intermolecular force of attraction, meaning these forces can easily be broken. And if they can easily be broken, meaning that the ability of this substance to form, to change into vapor molecules becomes high. And if it is high, therefore, at the end of it all, we have our vapor pressure becoming high. That's why we have seen even for temperature, if the temperature is high, meaning it is going to increase the kinetic energy of the particles, and therefore if it is increased, which means the rate at which the vapor is forming becomes higher. So which means the more it forms this vapor, the more we have our vapor pressure increasing. So the higher the temperature, the higher the vapor pressure. So that is how we have been able to explain that too. Okay, thank you. Maybe let me hear from Doreen now. We can put down the hand so that we get to know who has a question. Yes, Doreen.
Good afternoon.
Good afternoon.
So my question is, I just want to clarify on this issue. Can we join, like when we are giving the factors that affect vapor pressure, can we integrate the nature of the liquid and also the strength of intermolecular forces? Can we make it one answer?
Actually, it is one answer. You look at, are you seeing the screen? You see, the nature of the liquid is one point. So this is the explanation to this.
Okay.
The nature of the liquid is dependent on the strength of intermolecular forces. Which means when the intermolecular force of attraction is strong, meaning these particles will need much energy to change into maybe vapor. Are you seeing that? But if they are weak, which means they will easily be broken to form the vapor molecules. What does it mean? If form the vapor molecules, recall the vapor pressure is that end pressure exerted on the vapor. So, which means if a substance is in liquid, it has to first change into vapor. That's why we were saying that the stronger intermolecular forces, the lower the vapor pressure. But the weaker intermolecular forces, the stronger, or the higher the vapor pressure. Yeah. Okay. Good.
Thank you.
Okay, welcome. Okay, Linda now. Linda, as we wind up with the
Excuse me, sir.
Yes, please.
I beg that you throw more light on point 3.
Presence. Okay. Yeah, that's where we are going. Let me explain the presence of dissolved substance. Maybe before I tell you, Linda, are you the one?
Yes. Yes, sir.
You're the one? What do you think? What do you think, or how do you think the presence of dissolved substances or impurities can affect the vapor pressure? Keep your microphone on. We have whether Peace has. If Peace has the answer,
lost.
Okay, it's okay. But Peace, you unmute and you explain for us that. You unmute again. Okay. Hey, sorry. You unmute. I think there's an. Okay.
Okay. I also understand the question, but let me also try to explain that. So what I think about the of substance included is substance, how it can affect the vapor pressure. Quantify
your network is not clear.
I'm not getting her.
The sound is not very clear. Maybe if you can get somewhere where there is more network.
I get it.
We can't hear you very well. Okay, Wafula Elijah, you have the answer. You can help out there. Wafula Elijah.
So no, I had another question.
On factors.
Just just an inquiry to clarify
Yes.
where I drew my point of flammability. Now, putting it in everyday aspect, for instance, a pressure cooker. Now, you see the pressure cooker, I think it works on the same principle. So I was thinking if we had used another liquid apart from water, because I know it usually uses water, it would actually blow up. So that's why I was thinking about flammability to be a factor.
That's why you are thinking that?
Flammability can affect, but I got the clarity. So I was just confirming that I think this works as
flammability.
Yes, I understood it.
So can flammability be also one of the factors? That's what you're asking, Okay. I think there is an issue on the network. Maybe Ruth, you unmute so that you can get more clear. Yes, Ruth?
Okay. I wanted to answer. The first I wanted to answer who Wafula, but then let me first answer this, the person who asked for the explanation of the third point. Was it? They say
Yes.
they were asking for clarification on the presence of dissolved substances. When different substances dissolve, now for example in water together with the water molecules form hydrogen bonds between themselves. But when some substances are dissolved or impurities, they change or alter the intermolecular forces. So some may not bond with water via hydrogen bonding, but may bond in some other way. And it so happens that these bonds may be stronger than the hydrogen bonds that are within the water molecules. I'm using water as a case scenario. So when that happens, the rate of vapor pressure, the amount of vapor pressure will will reduce because of the stronger intermolecular forces of attraction. So or weaker. When the weaker molecule, when the weaker, we expect higher vapor pressure. So the variation in the intermolecular forces that have been installed by the impurities and the variation in the liquidity of the solution after having these substances in can bring variation in vapor pressure.
So the one which is having impurity, the impure substance and pure substance, which one is going to have a higher vapor pressure?
The impure one is going to have a lower, then pure will have a higher.
A higher. Okay. Yeah, so I believe you also had a question?
No, for that point of Wafula flammability, like I did some research, they say that vapor pressure directly determines a liquid's volatility. Okay, in regards to the way you explained it, is that as temperature increases, vapor pressure increases. So allowing more vapor to form and ignite, that's for the case of flammable liquids. He said it because you gave petrol as an example. So since petrol is volatile, so in presence, so the it's under Google. They say as temperature increases, vapor pressure rises, allowing more vapor to form and ignite, often measured by the flash point. So liquids with higher vapor pressure are more volatile and more likely to form ignitable mixtures, but that is in presence of what? Air. So without air or in a vacuum space, we won't have the flammability property being established. But when air is present and vapor pressure is high enough and achieved, then we can regard flammability as a what? As a factor affecting vapor pressure.
But now you recall, here we are looking at the other key points we noted. We needed a closed container. Are you seeing that?
Yes.
Yeah,
Yes.
so that's why we see the major key factors we will be having, it's maybe that nature of the liquid, the temperature, and then the presence of the dissolved substance or presence of any impurity. And as we have shared already, if substance is pure, for example, if you look at pure water and then look at another substance, water with maybe salt solution, maybe now this is water where we have added some salt. You find out that this one, which is very pure, will be having a higher vapor pressure compared to the one which is impure. Why? Because of these impurities that are coming in. But in this case, we look at the one which is non-volatile. The solute must be non-volatile, the one which you have added inside, if we are to test this one. Otherwise, if the solute is volatile, e.g., maybe like alcohol, which is volatile, you'll find out it will also contribute to the vapor pressure. So when you're testing this impurity which you have added, it should be non-volatile. Should be non-volatile.
So the impurity should have almost the same evaporation like point.
Because like the reason why we're saying this solute must be non-volatile, we're talking about the solute which you're adding maybe in this solution. If it is volatile, meaning it is also going to contribute to the vapor pressure.
Okay.
And therefore, you'll not be able to determine what you have been looking for. So that's why we say that it has to be non-volatile. Okay, I know because of time we may not go very far. But this is a good introduction that I wanted us to have for today. And then I'll leave you with some research questions. I'm going to show us what I want us to do research about, where we are going to start from next time. But let me first respond to everyone who is putting up the hand, and then we'll be able to close. Let me start with Malaika. Yes, Malaika.
Master, mine is not a question, but I wanted to explain of a pure liquid and impure liquid. So from my point of view, it is like when you dissolve an non-volatile solute, like that solute in water, when you dissolve in water, the solute like occupies the surface of the solute, preventing the water molecules to vaporize. So that lowers the vapor pressure.
That's lowering the vapor pressure. Good. Yeah, that is a good submission. That I like how people are now giving those nice submissions. Let me see now. I'm moving step by step so that I finish these hands which are up. Dr. Peace, but it will be faster.
Teacher, mine is a question. It's an inquiry. I would like to know, because I thought when there are impurities in a substance, like they tend to lower the boiling point of that substance or the vaporization point of that substance. So since the... Yes, teacher?
Yes, I'm getting you.
So since these impurities tend to cause breakage of bonds easier, like in terms of vaporization. So they tend to cause the breakage of bonds easier. Thus, maybe if it's a liquid, it vaporizes faster. So I thought since they cause a lower vaporization point, okay, for me, I was thinking otherwise. I thought that then the vapor pressure will be higher in an impure substance.
Actually, look at what you have explained already. Don't remove, because you see, you're saying that if there are impurities, are we there?
Yes.
These impurities, they lower the what? The boiling point or even the vaporization, isn't it?
Yes.
Are we saying that? Now, if they lower the
Yes.
vaporization to take place, what does it mean? It means that you call vapor pressure is the pressure exerted on the vapor, which means if we have a liquid, for us to get its vapor pressure, we must look at it must change from its state to the vapor form. Now, if it takes much time to form the vapor, do you think its vapor pressure will be high or low? Are you
If
saying
it
that?
takes much time, yeah.
Which means its vapor pressure will be low if there are some impurities from even that explanation that you have given us. I don't
So
know whether it is now.
I'm not yet contented. Okay, I thought since the vaporization point is lowered, it means that the vaporization is going to occur at a lower temperature compared to the substance. The vapor will be formed.
Okay, you keep your microphone on and you hear from Samsung. Let's hear from Samsung. Samsung, unmute. Hey, you unmute again, Samsung. We have like 2 minutes to end.
Sure. My question is here
Hey,
on non
I
on
wanted you
non
to answer. I wanted you to answer peace.
this
Did you?
about the impurities.
Yes.
Me, I think like the way you had explained it before, like when the impurity is non-volatile, when the impurity is non-volatile, that means that it's when the impure substance will be low. But in case the impurity is volatile, then for it will also contribute to the vapor pressure of the substance, increasing the vapor pressure. Unlike the one of the pure, whereby for it, if it's non-volatile and the solute is for the pure, the vapor pressure remain high. But in case it is impure and the impurity is non-volatile, it's when the vapor pressure will be low.
Okay.
Yes.
Thank you. Maybe to add something small so that peace can we can get it. She can get very contented now. So I just wanted to use this space. We're saying that when impurities are present, we are looking at when we add an impurity and when we have a pure substance. When we add an impurity, we are talking about when like a non-volatile substance is added. Why are we adding a non-volatile substance? Because if we put a volatile substance, we also contribute. So we need to use a non-volatile solute to maybe that liquid. So we're comparing these two between a pure substance and impure substance where we have added a non-volatile solute. Which one has a higher vapor pressure? So we're saying that the one with a higher vapor pressure is the pure one. Why? So we are saying that in a pure liquid, many liquid molecules, piece you need to pay attention there. Many liquid molecules at the surface can easily escape into vapor phase. That is for a pure substance. But when you come to an impure substance where we have added a non-volatile solute, now what does it mean? It means that some surface position in impure substance have been occupied by solute particles. So what does it mean? Fewer solvent molecules are able to escape. Thus, fewer, which means as a result, fewer vapor molecules will form, and thus the vapor pressure also becomes low.
Now I get you, TC. I've got it.
Actually, that's when we shall be moving directly now to RAOULT'S law, and we see those ones which deviate from RAOULT'S law later as we continue to discuss ahead. Okay, thank you. We cannot put the hand down so that we have these other people. I see those ones who are remaining. Okay, good, good. One person remaining. Domitia, and then we close. Domitia, you're the one who will lead us in the closing prayer after showing you your research work. Adubo, unmute. You're the last person.
Yes, sir.
Yes, please.
Hello.
You had a question? I can hear you.
Teacher, I had a question.
Mm.
Like, according to the lessons for 5 a.m., have they specified them, like, specifically?
About the what?
About the early morning questions at 5 a.m.